Let's look at the roots, otherwise known as the zeros, of a quadratic function and how that relates to the graph. We're going to allow imaginary and complex zeros, but it's going to be important to remember that only real zeros are going to show up as x-intercepts. And so we're going to see that very specifically in some examples here with quadratics. So we've typically expected quadratic equations to have two roots. And so let's look at an example. Very simple kind of example, x squared minus 5x plus 6 equals 0. And this one happens to factor. And so when we set that equals 0, of course, we get x equals 2 and 3. And so very nice, two real roots, real zeros. What does that mean about the graph? Let's go ahead and graph this and remind ourselves of what that looks like. So that's a parabola opening upward because it's got the positive coefficient in front, the leading term, and of course it intersects at 2, 2, and 3. Okay, great, not super surprising, but we already know there are two other really, really important cases, and I want to focus on those in this video. What if you had a rather special quadratic, x squared minus 4x plus 4 equals 0? Well, that's x minus 2 squared equals 0. That only has one root. We do say it has multiplicity too, and that's quite significant, and we'll remind ourselves of the graphical significance in a second. But that really is very different from having two different real numbers, and it's very different from having two different intersections with the graph. So let's see what that looks like. And of course, with that one root of multiplicity 2, it just comes down and touches the axis at x equals 2. So that's certainly a different case. What about x squared plus 1 equals 0? That is really, really different, because if we try to solve that, we're getting x squared is minus 1. If we didn't allow I, we'd just say that has no solution. Now we're saying, okay, that really has a mathematical meaning. There are two solutions, plus or minus I, but those are not real numbers. We should not expect the parabolic graph to cross the axis, and of course it doesn't. X squared plus 1, let's graph y equals x squared plus 1. So that's what the graph looks like. It's a very simple quadratic. It's just been raised up by one unit. And surprise, surprise, it doesn't cross the axis. So there's no inconsistency here. It's all very consistent. But this is kind of the most interesting new case. When we graph a parabola and we see from the graph that it doesn't intersect the x-axis, it's not that there's no roots at all. It's just that there's no real roots. And there's going to be, in that case, there's always going to be two complex roots, like in this case. So let's let the quadratic formula kind of take over and really justify that. So the quadratic formula, of course, is we've got minus b plus or minus root b squared minus 4ac over 2a. And I want to focus on the discriminant. So that's b squared. That's this interesting quantity. It's often called capital D. That's that interesting quantity inside the root. And there's going to be three cases for this. If we weren't allowing complex numbers, we'd just be like, if that's negative, we're done. We just say there's no roots, but we're going beyond that now. So there's three cases. We've got d greater than 0. Then that's our nicest case. We've got two real roots. That was like our first example above. We've got d equals 0, which is certainly interesting. And that's where you don't get any plus or minus. You just get the single number minus b over 2a. And that is the case of one root of multiplicity 2. And of course, so what's the graph going to do here? It crosses twice. 2x intercepts. Here, graph is going to touch. It's going to not cross at the single x-intercept. And then the most novel one that we were kind of avoiding doing anything with before most of the time was d less than 0. And we're going to get two complex roots unambiguously, because this negative number that b squared minus 4ac, the square root of that is going to be something times I, and we're going to get a plus or minus something times I. So we can predict that in every single d less than 0 case, we're going to get two complex roots. Okay, and so let's look at another somewhat more complicated case. We'll modify one of our examples above. Let's say we look at x squared plus 4x plus 5 equals 0. So we're going to use the quadratic formula. Denominator is just 2. We get minus 4 plus or minus root b squared is 16 minus 4 times 1 times 5 is 20. Okay. And we're getting minus 4 plus or minus root minus 4 all over 2. Minus 4 plus or minus, we can take out that 4 because it's a real square, 2, and then I get root minus 1, and that's our abbreviation for that is I, all over 2, and then that simplifies to minus 2 plus or minus, actually, yeah, okay. Actually, you know what, let me make that a minus, because I forgot we had a minus. All that changes is this guy. That's a little bit more like the example I had before. Okay, so that's exactly the example I had before with a 4 changed to a 5. Forgot about the sign. Okay, so our roots are 2 plus or minus I. And notice there's a special form here is that the only place the I is coming in is from the square root of the negative here. That's always after a plus or minus. The rest of it, this is always going to be the real part, giving me this the minus b over 2a part. And so the real part of both the roots is always going to be the same, and the imaginary part is always going to be opposite. And so that's what's called complex conjugates. I think we've seen this before, but let me remind you, the complex conjugate of a complex number a plus bi is just a minus bi. If you symbolize, our book doesn't do this very much, but if you symbolize, it's like with one letter to summarize a complex number, then this is usually, you put a bar over it. Let me see W, for example. It'll show up, the bar shows up better. The notation that people use for that is you put a bar over it. And so the bar, the complex conjugate of that is going to be a minus bi. And so these are of two numbers that are complex conjugates of each other. And so this is a general fact. The two complex solutions for a quadratic, when they are complex, and that's if you start out with real coefficients. You can define complex quadratic polynomials and any polynomials with complex coefficients. We really don't go there at this level. It's just kind of more sophisticated as to why you would even want that. We're letting the complex numbers be forced on us as the solutions of these guys, and not actually preloading the quadratics themselves. So the two complex solutions for a quadratic with real coefficients are always complex conjugates of each other. So they're not two totally unrelated. Okay. And that generalizes to higher degree polynomials. We'll talk about that very briefly. We don't have a lot of time. So this gets pretty formal here. What does this mean for the graph? Let me just show you real quick. And I want to show you the relation to factoring. So let me switch over to Desmos for that. So here's Desmos. Okay, so let's just look at some examples. So here's x minus 2 squared, exactly what we had before. That's this very special case, and it's going to be the boundary case between the real and the complex world. So that's y equals x minus 2 squared. It comes down at 2, 0 with multiplicity 2. That's groovy. All right, let's switch over to, let's say x minus 1 times x minus 3. So here I'm I picked two roots that were still symmetric around 2. And what you can see is that that's actually just dragged it down. How about x minus 1.5 times x minus 2.5? So here, by actually writing them in factored form, we've seen this before. You can design these guys to have the roots you want. And in fact, all I'm doing is I'm dragging that same polynomial up and down, but that's by specifically picking those roots to be symmetric around x equals 2. Another way to say it is I'm keeping the axis of symmetry to be x equals 2. Okay, well, let me show you kind of an animation of that. What if I had, I'm going to put a slider in here, and notice what I'm doing. Let me show you, give you a little more room. I'm picking one of the roots to be 2 minus a number. It's going to be usually small. And the other root to be 2 plus a number. And this is going to encapsulate all the cases we've seen before. And if I change that slider, look what happens. It may seem like the slider is designed to move it up and down, but that's not really what it's doing. The slider is designed to pick certain roots. So here's minus 1 and 5. Here's 0 and 4. Here's 1 and 3 that we saw before. Here's 1.5 and 2.5. And then as I crank the slider down, it goes to 0, and I get that double root case. So one interesting thing, though, is that if I use the slider to create 2 real roots, if I just show this to somebody, again, it's going to look like my slider just pushes it up. Just kind of pushes the thing up, 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 up. And then people are going to be like, why did it stop? Well, if I create this with real roots, I have to stop there. If I want to see it lift off the axis, I've got to give it complex roots. So let's go back to like a specific example. What if I had y equals x times, this is a little more complicated to look at, 2 minus I is one of the roots, and 2 plus I is another one of the roots. I claim, we'll go back to the other program in a sec, and I'll show this very explicitly. I claim that's exactly a way to create something where the quadratic still has axis of symmetry x equals 2, but I've made it lift off. Of course I've made it lift off because the roots of this guy, because I factored it as x minus this complex number times x minus this complex number, I'm looking at the complex roots of this quadratic. This will be 0 exactly when x is either 2 minus I or 2 plus I. Those are the kinds of things. Notice it's a complex conjugate pair. Those are the kinds of things I would get out of the quadratic formula. Here I'm reversing the story. I'm designing it to have these roots. What if I don't get so aggressive with the i's? I put in a smaller amount of I. This would be something where the roots are 2 minus I over 2 and 2 plus I over 2. Turns out, and we'll have to go back and do the algebra to really, I think, convince you, that that exactly gives us this polynomial that's just barely off. Because these guys are getting kind of closer-ish to being real numbers, that imaginary part has gotten smaller. Let me show you the animation of that guy. So here, notice what I've got here. I've got something where I design a quadratic that it's, by writing it in factored form, I've made sure that its 2 complex roots are 2 minus some little bit of I, and its conjugate 2 plus that same little bit of I. Now if a equals 0, that's of course what we saw before. There's no I, but now I make it lift off by adding in that imaginary part. So that's the other part of the story. Let me actually just activate both of them. That the blue ones, that's what happens when you create 2 real roots that are symmetric around 2. And then the red ones are what happens when you create 2 complex roots that are symmetric in a very different way around 2. So let me go back and really show you with just one of these examples. Is it really true that if I just multiply this out, this is really just going to be multiplying out, but we're going to have to use our complex arithmetic skills. This should be some nice real polynomial, and it should be something we can recognize as having vertex. Let's see, this was the claim. This was something that had vertex 2, 1 in particular. Does it really? So let's see, it's getting a little long, but bear with me. Okay, so we're going to get x squared minus, okay, we got to be careful with our parentheses, 2 minus I times x. Let me kind of group this all together. And then another 2 plus I, 2 plus I times x. And then plus, so we got minus times minus is plus, and then 2 minus I, 2 plus I. Oh, hello. Okay, the x squared's fine. Minus, okay. And we've seen something like this before. Ooh, I'm going to get a minus ix and a plus ix. Those cancel each other. And surprise, surprise, hey, all I get is a minus 4x. So this is a very common thing. One way to see that maybe a little more clearly is I could factor out that x first. And I'm just adding a complex number to its complex conjugate. That always produces a real number. Now, what about this guy? I've got to FOIL this out. 4 minus 2i plus 2i. Hey, it's difference of squares. The mid terms always cancel out. And then a minus I squared. And I think I know what I squared is. So these guys are canceling. And minus I squared is plus 1. And so we get plus 5. Hey, I can complete the square on that really easily. That is x minus 2 squared, which would be x squared minus 4x plus 5, plus 1. And indeed, that is a parabola opening upward with vertex 2, 1 as advertised.